All right, we've been looking at constructing logical arguments. In previous lessons, we looked at two different argument forms, deductive arguments and inductive arguments. What I want to do now is start to give you some very specific deductive argument forms. So these are, again, only going to apply to deductive arguments, and they are valid argument forms. You can use these basic forms, plug in various terms, and create deductive arguments from them. All right, so we're going to continue on looking at argument forms, but we're going to focus now on looking at very specific deductive argument forms that you can use to construct arguments. All right, so let's remember that deductive arguments we would call syllogisms. Syllogisms have exactly two premises and one conclusion. And these syllogisms, again, are rules that, given the truth of the premises, the conclusion necessarily follows. And this is going to be true for every deductive argument form that we look at. All right, I'm going to give you a symbolic representation. I'll give you an example. I'll give you the Latin name for each of these forms. And then you can use these not only to construct arguments, but as you're doing any kind of reading, both in literature, newspaper, anything, anybody that wants to make an argument, you can start to look at the argument that they're making and see if you can find the symbolic representation, the form of those arguments that you're reading about. Okay? So the first argument we've seen already in a previous lesson. It's called modus ponens. Literally means the mode of putting. The mode of putting, the modus ponens argument. All right, the form of the argument looks like this. Actually, this is the symbolic representation that's verbalized in an English sentence. We say if P then Q, and here's why we call it the mode of putting. We're going to put forth the antecedent of the conditional in the first premise. We're asserting it. We're claiming it's true. Right? So we're going to assert the antecedent here, and then that allows us to conclude the consequent. All right? Here's an example. If Jerry grows a mustache, then George grows one. Jerry does grow a mustache. Again, asserting that antecedent in the first conditional, first premise. We can then conclude, therefore, George will grow a mustache. All right? And then here's the symbolic form of that argument. P arrow Q. Assert P, conclude Q, the modus ponens argument. And remember, you can insert any value, any simple or compound statement for P or Q, and the structure is still valid, right? And obviously you want to use true premises there so that you can conclude something that's also true. But this is the modus ponens form. It's always valid, and it's a deductive form of argumentation, right? Modus ponens. Let's look at the next one. This is called the modus tollens, or the mode of taking. The mode of taking. The modus tollens argument. And again, another valid argument form. This one says, if P then Q, conditional in the first premise, we're going to negate or take away, that's why it's called the mode of taking, we're going to negate the consequent in the second premise, not Q. Therefore, we can conclude with logical necessity, therefore not P. Therefore not P. If P then Q, not Q, therefore not P. Notice that it's different from the modus ponens in that in the modus ponens we're asserting the antecedent and concluding the consequent. Here we're negating the consequent and asserting the antecedent. All right, here's an example. If you are in college, then you are exhausted. It's not the case that you're exhausted. Therefore, it is not the case that you're in college. Now, you might say that there's something, what does that mean? How can we can say that it's not the case that you're in college based on the case that you're not exhausted? Because the first premise tells us that it's necessarily true that if you're in college, then you must be exhausted. Since you're not exhausted, it's impossible that you're in college. Okay? That's what the form of the argument, that's what a deductive argument allows us to do. All right, and here's the symbolic form. We say P arrow Q, tilde Q, therefore tilde P. That's the form of the argument. You can plug any value, compound or simple statements for P or Q, still have a valid argument form, and construct a valid logical argument. Whether the argument of sound, of course, is going to be dependent upon whether or not your premises are true. All right? Now, I'm going to give you some real-world examples of modus tollens at work. All right? You can see how in literature you can actually pull these argument forms out when you're reading something in a book or a newspaper or whatever. Here's a couple of examples of a modus tollens argument in literature and in a scientific publication. First one is from Sherlock Holmes. All right? Here's what Holmes says. A dog was kept in the stalls, and yet, though someone had been in and fetched out a horse, he had not barked. Obviously, the visitor was someone whom the dog knew well. That is a modus tollens argument. It's the mode of taking. You can actually pull out the premises here and stick it in that logical structure, in that form, and see how it is a modus tollens. In fact, if you want to pause your video, try to do that. Try to pull out the premises of Holmes's argument and put it in a modus tollens form from the previous slide. See if you can do that. Here's another example. If the universe were infinitely old, there would be no hydrogen left in it, since hydrogen is steadily converted into helium throughout the universe, and this conversion is a one-way process. But in fact, the universe consists almost entirely of hydrogen. It is not the case that, even though it looks like a positive statement, Hoyle is actually reversing the truth value of the consequent in the first premise. Thus, the universe must have had a definite beginning, according to Hoyle. All right, very interesting argument that is a modus tollens argument. Again, if you wanted to pause the video, see if you can put the argument into modus tollens form in the format that we looked at before. But these are two examples of modus tollens, the mode of taking argument in literature and in a scientific publication. There's another type of modus tollens that we can make, another type of argument, and I want to look at that as well. Have you ever had a conversation with someone and said, okay, for the sake of argument, I'm going to assume you're right. Let's see what happens. Let's see what happens if I assume you're right. That's a modus tollens type of argument, and it's called a reductio ad absurdum. That's the Latin name. Literally means a reduction to the absurd. A reductio ad absurdum. But it's a type of modus tollens at the end of the day. All right? So let's suppose you want to prove proposition P is true. You assume its negation. You assume that not P is true or that P is false. Okay? Remember, your goal is to prove P, but you're going to start by assuming that P is false. From that assumption, you derive another proposition. And that proposition has to be false because it's absurd. Okay? So if not P is true, this other thing turns out to be also true, but that other thing, that Q, is false, or because it's absurd, therefore P must be true. In other words, it's impossible that not P is true because it involves a contradiction or an absurdity. That's a reductio ad absurdum argument, and it is a type of modus tollens. Now, if this is a little confusing, let me give you an example to show you how this actually works in the real world. Let's suppose you want to prove that the Earth is round. You start by assuming its negation. So you say, suppose the Earth is flat. If the Earth is flat, it has edges, and it would be possible to fall off the edge. In such a case, people and animals regularly would be falling off the edge of the Earth. But that's a ridiculous thing to believe, because people and animals don't actually fall off the Earth. It's an absurdity. So assuming the opposite of the thing you want to prove, that the Earth is round, assuming that the Earth is flat, we end up with an absurdity that animals and people are constantly falling off the Earth. That's just not true. Therefore, it seems clear that the Earth is not flat or the Earth is round. That's our original premise, proposition that we want to prove to be true. So this is essentially a modus tollens argument in the reductio ad absurdum form. And anytime you say to a friend or someone else that you're talking with, a colleague, anytime you say, okay, for the sake of argument, let's assume you're true, your conclusion is true, you're using a reductio ad absurdum argument, which is a form of modus tollens. Okay? So that's a very interesting way that we can use that same type of argumentation form in a little bit of a different format. All right, the third one I want to give you is called the hypothetical syllogism. The hypothetical syllogism. And you can see from the name probably that we're going to be working with conditionals here. All right, the form of the argument looks like this. If P, then Q. If Q, then R. Therefore, if P, then R. All right, so we're taking the consequent of the first conditional and making it the antecedent of the second conditional and introducing a new consequent. And then in the conclusion, we take the antecedent of the first conditional and associate that with the consequent of the second conditional in a new conditional in the conclusion. All right, so here's an example. If you're a Monty Python fan, you'll recognize this. If she's as light as a duck, then she's as light as wood. If she's as light as wood, then she will float in water. Therefore, if she's as light as a duck, then she will float in water. And again, if you look at this intuitively, you can see how this works, right? By making these associations between antecedents and consequent, we can actually come up with that third conditional in the conclusion, and you can see how all that works together. All right, and here's our symbolic form. If or P arrow Q, Q arrow R, conclusion, therefore P arrow R. And that's our hypothetical syllogism. All right, so now we have three. We have our modus ponens, we have our modus tollens. We saw a couple of different forms of that, the reductio ad absurdum. And now we've got our third called the hypothetical syllogism. And we're going to end with one final one called the disjunctive syllogism. The disjunctive syllogism. If you remember from a previous lesson, we looked at the disjunctive symbol, the disjunction symbol. Now we're going to look at this, that symbol being used in a syllogism. The form is P or Q. In the second, for the first premise, in the second premise, we negate one of the disjuncts. It doesn't matter which one. But whatever disjunct we negate, that then allows us to assert as true the other disjunct. Okay, so P or Q, not P, therefore Q, or we could say in the second premise, not Q. That would allow us in the conclusion to assert, therefore, P. Right? Example, either the Beatles are playing tonight or the Rolling Stones are playing. It is not the case that the Beatles are playing, so it must be true then that the Rolling Stones are playing. All right? Or we could say it is not the case that the Rolling Stones are playing, therefore it must be true, logical necessity, right? The conclusion necessarily follows from the truth of the premises, therefore it must be true that the Beatles are playing. All right? And here's our symbolic form. We say P, V, P wedge, Q, tilde P, assert as the conclusion Q, or tilde Q, assert as the conclusion P. So now what we have, you have added to your toolkit 4 deductive syllogisms. Again, you can take the symbolic version of these, plug in any simple or compound statement to any of these syllogisms, and you have a valid argument. If you have true premises for your arguments, for your syllogisms, you're going to end up with a sound argument at the end. And you can use these syllogisms together to build complex arguments. And we'll see how this is done as we move throughout the course. Again, I want to call your attention to the similarity between what we're doing here in formal logic and what you might do in a computer program. If you've written in any modern computer language, you have used these constructs. You've used conditional statements. You've used conjunction statements, disjunctions. You've used those in your computer programming language to actually have a logical flow to your program. And that's what we're doing with language. That's what we're doing with concepts. We're applying those logical flows to the way that we think about the world, the way that we think about our ideas, and it's very, very similar, right? You're going to use the same constructs in programming as you're using in formal logic. This is why learning formal logic can actually help you become a better programmer, because you're going to learn how those things, both of those things work together and work in synergy. So as we move throughout the rest of the course, we're going to start to apply some of these concepts to what we do in computer science.